979, distribute coins in a binary tree. Given the root of a binary tree of n nodes, each node in a tree has node.val coins, and there are n coins total. Ooh. In one move, we may choose two adjacent nodes and move one coin from one node to another. The move may be from parent to child or from child to parent. Return the number of moves required to make every node have exactly one coin. Okay. I think my thought process here is that, well, let me look at the problems. I think my thought process is you never, my thought process is you never want to have more than one coin at any node, right? So I think we're talking about invariance, and that's going to be the invariant. And what that means is that at every turn, you will always try to remove, or the number. You always move your coins either to the left or to the right. Yeah, binary tree, left or to the right. The number of coins that's required, right? So my initial thought on this one would be to count how many coins that the left subtree needs, and then count the number of coins that the right subtree needs, and then distribute them that way. And that function is just the number of total coins in the left subtree and the right subtree. And there's another thing that I will point out in a second, but that should be good enough. And then you kind of have, yeah, I'm just thinking about and that would be how you cascade coins. In this case, like for example, you do one left, one right. But I think the tricky case would be something like this, right? And in something like this, there may be fancy ways of doing it, but how I would think about it is still you count the number of coins on the left and the number of coins on the right, and oh yeah, that's what I was going to say is that you could I don't know. I want to say this in a more precise way because I don't want to mess up. That's what I'm thinking. But you could actually have negative coins, assuming that you will get it from your child. I think that's bring out the pain again. Yeah, I mean, I think the way I think the thing so there are a couple of things, right? Which is kind of to get the coins back from your child, but another part of that component is the number of moves. So that separate the coins for a second. That's the number of coins that you have to move, right? Or from this node, right? So for example, let's say you have something trickier maybe, but even for this case, right? Example 3. With your left subtree is 0, your right tree is 2, right? And what that means, or sorry, how do I want to do it? Well, maybe this is actually instead of 0 and 2, the way I would do return is actually the balance of the nodes minus so yeah, which is the number of nodes minus the number of coins it have, right? So in this case, your left subtree will be -1, and your right subtree is 1, right? And then your root in this case is actually 0, which is fun. But that means that because of this case, that you could do the math, which means that there will always be at least one coin moving from the right to the left, right? And it takes one move passing through so here you don't think about things in terms of each coin, because that's really hard to kind of keep track of. But what I would think about is how many moves or how many times is any number of coin passing through this current node, right? And in this example, well, on the right subtree, because and it's always going to be let me double check the constraints. So each in this, so what I'm looking for is that just want to make sure that there are enough coins for everybody, because then maybe some of that logic breaks down. You have to check for it. But okay, it seems like there's n nodes and there are n coins, so that should be okay. So then the invariant is that well, if the right subtree has one excessive node, then then and the left subtree has one required node. That means that one coin will go from the right to the root, and then root to the left. So that's two moves, right? So that's how I think about it. And then you do the math that way, and then recurse. So you have a recursion based on that. And similarly to here, which may be a trickier one, but to think about. But your left is +2. Your root is -1, and then your right is -2, right? In this case, or -1, sorry. So in this case, you have 2 going from left to the root. We keep 1 here, and then we have 1 more to go to the right. So that's 3 total, right? So that's how I would do the math. So yeah, I hope that I explained my thought process a little bit, because I think I don't know if I explained it clearly, to be honest, because I'm solving it with you guys, and it's not like this is not prepared, so it's not me being like, let me just read a solution off my Larry's list of pre-prepared solution. So I did kind of change the problem a little bit. I think instead of I think how I think about it is kind of just keeping track of these balance, and instead of thinking about it from, hey, here's a node, or sorry, here's a coin, or here's a tree, I guess, and how do I get to distribute it? What I think about is, well, how many coins have to pass through this node from left to right or right to left, and keeping track of the current root, and then that's how I would think about it. So I think that's the thing, is that so this is going to be the balance. So I maybe hand wave the recursive part a little bit, but this is only just your left balance and the right balance, right? So you don't the state here, for example, now looking at example 4, because now there's 2 depths, right? By the time it gets to you, or by the time in this case, it goes full up. By the time it gets to the root, it only actually has, like the balance that goes up is that, oh, I only have 1 extra balance, right? So then in your root case in here, your left is actually -1, your root is 0 because you already have a coin, and your right is equal to +1, right? Oh, sorry, the other way. My fault. And in this way, you can also see the same thing where, well, this takes 2 moves from left to go to the right, and then you just keep track of moves in somewhere else, right? But this root costs 2 moves. This root costs 2 moves. That's a mouthful. But yeah, cool. I think that's enough for me to get started. Yeah. Give me a second. Let me think about it. I think that's all my edge cases. I think that I would also, to be honest, kind of like full disclosure, is that like I don't know how easy this is, in the sense that I think I struggle a lot with the maybe not in this problem, because I think I've solved something similar, but I definitely feel like in dynamic programming that this comes up a lot, where like, how do you know your substructures are optimal? And I think that's kind of the question that you're asking right now. And for viewers, just to be clear, C-level executive asked, you need to pass the state of the depth of the coins, as well as the number of coins already moved. Yeah, and I think the state part is always hard for me, especially when it comes to dynamic programming, is whether like the substructure is optimal. But I think for this, actually, I think to kind of cheat a little bit, which is in the programming detail, which is important, is that you could actually just store it in a global, because your moves, like, because in this case, you just try to, I mean, you could do it in different ways for sure, but the way I think about it is like, you could actually even store, like what we were talking about, like given these things, you could store, say, like in the tree node, a moves thing that like, hey, moves in this node is equal to 2 in this case, and then you just wanted that for search to kind of, or just like a simple recursion thing to sum up all your moves, and then that'll be your answer, right? So that's also not that bad. But I would say also because it's summing, meaning this, is commutative, meaning you could sum them in any order. I would actually just have a global variable, and that's why I'm going to start now with sum move 0, 0. I would have a helper that's something like maybe just called calculate moves for a node. Let's go a node, and then what's the number of moves, right? For a given node, how do we code what we just said, right? Well, if node is none, we just return 0. Yeah, that's fine, because that's the default thing. And then otherwise, left, let's just call it left balance because of what we said. So left balance is equal to calculate moves of node.left, and we don't have to care about nones. Right balance is equal to calculate moves, node.right, and then root balance or node balance maybe is equal to what is it? Oh, node.yu minus 1, right? And then now the number of moves is just equal to, so we just add this to the moves. I think now we have to call non-local moves in Python. It's just equal to the number left going through the node. So that's just left balance plus node balance plus right balance. And actually, the thing I have to is that right? I guess they could both have excess, so I have to figure out how the way to. No, I think this is right actually. We need the absolute value for the number of actual moves. I guess we didn't need it for this one, but because they could actually both be odd, right? So the tricky thing is, well, what do you return? You return not the number of moves. So I guess this naming is terrible actually. Calculate balance. So, my bad, friends. Yeah. So we. So what is the balance of this node? Is well, I think it's just left balance plus node balance plus right balance, right? Something like that. Maybe off by one, or maybe I could. I think right now I'm worried a little bit about the signs, because you could have something like, well, I don't know the thing, but you could have something like, and I guess that I could test this. So, but you have something like 0 or just one at top. And you have a left tree, or you have a right tree. Where's my thingies? You have a left right tree. Whoops. ASCII on this hard. And say you have like your right tree needs say 5, like whatever, or just 3, and then your left tree would have, well, this node has 1 for itself. ASCII art is kind of hard. I don't know why people spend so much time in it, but then you have like let's say 4, or let's say it's just 2 and 2, right? Is that enough? No, I need 1, 3 here. And then balance here at this node would actually be, so this gives me a 2. Yeah, this should give me a 2. This gives me a 1. So this will give me a 3 on this node plus the current one. So this is the balance, and then you keep going up with the 3. I think that's right, maybe. Okay, let's try it out. balance root, and then return moves. So calculate balance of the root should always be 0. We could even assert that maybe. Let's play around, at least in the test cases. All right, let's test this out. Oh, no's. I messed this up. I had to do more complicated math, I think. I forgot about the root case. I was too focused on the other cases. Yeah, so this is, so no balance is 2. So we definitely need to do 2, but then the left balance and the right balance. So maybe it's not that. There's some cases on this. Give me a second to think how to resolve the balance. It's just -1 and a -1. So I sum all that by, for whatever reason. I think you, well, let's say left. So left balance is the number of moves to move from the left to here, or from here to the left. You're right on that one. Maybe I don't need to know balance because that's implicit in the left and the node. I think you are right. Whoops. Thanks. Thanks, cool guy. Thanks for debugging. But yeah, I think speaking to your point, C-level executive, is very tricky. But yeah, because you only calculate the moves from your left to the right, and then if you count the node balance that's at your current node, then you're double counting it. But I think, I was just focused on like these cases, so I didn't really think about that one through, which I should. It's no excuse. I'm just still trying a little bit. But let's look at a little. Let's make sure it works for our test cases first before I ramble on about how correct this is. Cool. I mean, I'm relatively confident. I guess I might as well put this, the thing that I, oh, what's my ASCII art? I forget my ASCII art. Okay, fine. It's too far back. There's no undo. Okay, fine. I'll just submit then. Cool. Oh no, I didn't do it in 0 millisecond. I should have done it in Java. But yeah, how do I want to? I mean, I agree with that tricky. So yeah, so I think I explained this problem and I was of it enough for the postmortem. But I think separating the moves. Okay, you're definitely not wrong. I mean, I think you could still figure out the moves in a good way. So I think another way I would write it is something like, I mean, at least in Python, you could return a tuple. So you have something like, oops. Let's just say 0. It doesn't matter. Maybe a name tuple, that'll be better. But you could still do something like, right? Because I think all the recursion still happens at the top level, right? So you could definitely still, this is not right because of how I have to do the moves. I have to keep track of the moves. So left moves. So I try to rush it too much. Also, maybe this would have made it more clear though that I didn't need the current node moves. But right? So you have something like that, and I think that would be uh, I think this would be good enough. Whoops, I messed up the bracket on the tuple. Just a little bit, but you get the idea anyway. Um, I'll just okay. Oh, because I forgot to change the base case. Hmm. Oh no! Whoops! Did I not? I was wrong. Well, it's always 0 because I never added. Where did I add the 1 before? Uh, oh, oh, because oh no, this is right. It's just that I copy and paste stupidly, but also I needed to add this. If you, okay, fine. I mean, maybe I'll just use another variable to make it clear. Is it going? So I try to be a little bit too fast, right? But oh, but yeah. So this should be right. I mean, that's kind of with recursion. You could still do it with recursion without separating it. I think. Um, I mean, I did it the other way just because I don't know, like, because one of the property with summing is that happens. But like you can merge them in all the ways, and it still sums to the same thing, right? Which is a core concept in many things. But definitely, if you have a different function that may not be, you can merge in different pieces, then there are other ways to think about it as well. But yeah, I mean, maybe I hope this particular example is easier to show how the moves are kind of part of the calculation. Um, but yeah, because that's just the number of moves. But yeah, you have to separate out them as kind of two different things. Maybe that's what you mean more. Which, yeah, I mean, I agree with you that I don't know. I don't. Well, first of all, I don't think it's easy. I think this is a problem that uses stuff that I think people have seen before if you're like into the competitive programming stuff like this. But I wouldn't necessarily say like this is way intuitive. It's intuitive if you've seen it enough times, obviously. But this kind of concept where I think the way I think about it is okay. Instead of thinking about instead of thinking about coins and how coins move, I'll think about like, I mean, like, I think I mentioned this, but I still want to put more emphasis on it, which is that given a node, how many moves are going, like how many coins are coming in and how many coins are going out, and basically that's the case, and then you can sum the previous moves recursively. Uh, yeah, because left balance is the number of things going in or out if it's negative or whatever of the left and so forth. And the big key here is also just to make sure that the n nodes in n coins thing. This is the only reason why it works. I mean, it would mostly work in other cases, but you have to do some math and depending on the constraints and stuff like that. Maybe return -1 is not possible, but that's probably also like a straightforward depth of search and checking for the number of things you counted or something. So yeah, cool. As for an interview, I feel like this is more brain teasery. So even though there is trees, I think the thing with the one insight is that it's kind of hard to work your way through if you haven't seen similar problems, which is the invariant is very tricky to kind of understand, and I think the concept of kind of moving coins backwards, which is what a cool guy was moving to, is kind of non. It's not easy. Put it that way, right? It's very hard to be like, okay, it's because I think, yeah, I think I kind of alluded to this, but I didn't find a good way to say it. But I think the way now that I have a better, now that I've been talking about this farm for so long, uh, instead of thinking about like, okay, here's the root, you move the coins down. Okay, everyone knows that part. Like, if all the coins are on the root and there are no coins anywhere else, everyone could think, well, like, that's just standard depth of search. You just kind of, count the number of subtrees and so forth, right? But what if you have a case like this or a case like this, right? And I think that's the part that's tricky. And what I think about, and I think to be frank, I did not talk about this in a good way because this is very hard. And I think is that instead of looking this as the root getting 3 coins from, I think that's how I would categorize it as instead of the root giving the child or getting 3 coins back from one of its child, the way I would think about it is the coin is giving -2 coins to one of his child, and or in this case, just -1. Sorry, -1 coin to the left and 1 coin to the right. And how many moves would that take? Hopefully, that's a little better. And in that case, actually, in this case, it's -2. Sorry, I was right the first time. It's -2 to the left, and then one coin to the right, so that to make it even. And it's like a negative edge almost. And once you have that intuition about kind of of kind of passing an edge, but in reverse in a weird way, but negative of that, then it becomes a straightforward top-down recursion. And that's what I try to do with the balance, I think. I use the word balance, which is maybe has a better intuition, or at least a real or easier real life, understanding of that word. But where like I think having a negative edge and stuff like that is more like CSE, but maybe it's harder to understand if you don't already haven't seen it before. But yeah, I mean, and I would say like that's kind of an advanced topic. I don't know if I would see this, but I would say recursion and trees are pretty standard. So that part I would expect to see on an interview. But this other part, it's really tricky. I don't know if I would necessarily. But yeah, hope that okay. I think that's what I have to say about this problem. And also, I hope this is obvious. I didn't actually say it, but I hope this is. I mean, I don't hope it is, but it is O of n because you only check each balance. Sorry, each node. You only do constant number of operations. Or this is O of n. So or this is O of 1. Or because you only do each node once effectively. So it's O of n, and it requires technically O of depth max space, O of n new space, if you want to call it that, because we put stuff on the stack. So it's not O of 1 per se. Though some people have been kind of bad about saying it that way, but you do put like all these things on the stack, right? So so yeah. That's how I have about this problem. Let's take a quick look at the solution, actually. That first search, I mean, that's what I did. Is there another way? I just approach 1 and only approach 1. Oh man, their code is even cleaner than mine, but same idea. I mean, well, actually, this is pretty much exactly the same as my first idea, except for they wrote it in a much cleaner way, where I put the moves outside, and then this is just that. So there's a -1. Oh, I guess I put that in node balance. That's where my -1 is. And then everything else is about the same. Actually, everything is exactly the same. But yeah, cool.